Alright, in this lesson we're going to be learning how to solve equations of the form z to the n equals w, where w is a complex number. So as an example, where we're going to be heading to, we need to be able to solve something like z cubed equals negative 2 take away 2i. So we know there should be three solutions to that, because z cubed, this is really a polynomial. Z cubed minus this stuff equals 0. It's a polynomial. We should be able to solve it and get three solutions. But how do we do that? Okay, we're going to use a method going back to Moivre's theorem. I'm going to give you some steps that we're going to use, and then we'll actually go through this particular example and work out how to do it. So step number 1, if we're solving z to the n equals w, we need to express w in polar form. So you can see how important those earlier lessons in this unit were. So in other words, we'll need to express the negative 2 minus 2i, that's the w in this case. We need to express that in polar form. That is r cis theta. Step number 2, we need to realize that r cis theta is actually equal to r cis theta plus 2k pi. Now what that means is this: if you imagine r cis theta, your complex number may actually be here. Okay, and theta in this case will be the angle there. Okay, now that I get to the same place, this r cis theta might actually be this complex number here, but if I add any multiple of 2 pi, in other words any full circle, I'll come back to the same point. In other words, r cis theta could be the same as r cis theta plus k lots of 2 pi. We just wrote it as 2k pi, but it's really k lots of 2 pi. In other words, any multiple of 2 pi. We say that k must be an element of the integers. Okay, in other words, k could be 0, 1, 2, etc. Can't be fractional numbers. All right, step number 3. If z to the n equals r cis theta, okay, that's what we're starting with. Z to some power equals some complex number, theta plus 2k pi, okay, allowing for any multiple. Using de Moivre's theorem, z, to get z out of this, I need to raise it to the power of 1 over n. Okay, because I've really got z to the n, I'm raising it to the power of 1 over n, and that gives me z. So that's this thing to the power of 1 over n. Now that is r to the power of 1 over n, cis 1 over n times the angle. 1 over n times the angle is that. Theta plus 2k pi times by 1 over n, in other words divided by n, where k, remember, is 0, 1, 2, ... Now you'll know how far for k to go when we do a specific example. And there we will have our solutions. We wanted z, we've got z equals this. Now how will we get our three solutions? Our three solutions, which we know we need to get, comes from, I mean, this isn't going to change, theta's not going to change, but where our three solutions come from are different values of k. that we put in here. K could be equal to 0, K could be equal to 1, K could be equal to 2. And if we let K be 0, 1 and 2, we will get 3 different values for Z, which will be our 3 solutions. If we kept going and put K equal 3, 4, 5, 6, we would get all the same solutions repeated again. But we would get 3 unique solutions just with our first 3 K values. If we were doing Z to the power of 4, then we would need K equals 0, 1, 2 and 3. We'd need 4 different K values, 0, 1, 2 and 3. Okay, so let's have a look at this specific example that we've got and see how we do this. So solve Z cubed equals negative 2 take away 2i. So first of all we need to express that in polar form. So let's let W, let's call this a name, call it, instead of calling it Z cubed, let's call it W, negative 2 take away 2i. And we need to express it in polar form. So negative 2 take away 2i is going to be down here somewhere. Negative 2, imaginary and real. Okay, so first of all, the magnitude of, or the modulus of W will be the square root of 2 squared plus 2 squared, which is 4 square root of 8, or 2 root 2 if you like, is the magnitude. And the other thing we need is the angle. So theta will equal the tan inverse. Remember what we said earlier, forget about whether it's positive or negative. Tan inverse of 2 over 2, which will be pi on 4, 45 degrees. Theta equals pi on 4. But we need to assign this as an argument. Therefore, argz equals, now the quickest way to get to this point is coming back this way. This is 4 pi on 4, working in quarters, since we had quarters here. So coming back this way, if this is pi on 4, that little angle there, then altogether that must be negative 3 pi on 4. Okay, therefore W equals square root of 8 cis negative 3 pi on 4. Okay, let's turn the page. But W also equals root 8 cis negative 3 pi on 4 plus however many times we want to go around here in terms of full circles. I can, to my argument, I can add any multiple of 2 pi. So I could write 2 pi times k. Alright, normally we write the 2k pi though, where k is equal to 0, 1, 2, dot, dot, dot. Therefore, Z cubed equals, going back to this, instead of negative 2 minus 2i, Z cubed equals the square root of 8 cis negative 3 pi on 4. Now what I'm going to do here is actually get a common denominator. So I'm going to, this is over 1. So let's get a common denominator of 4 plus 8k pi. So 2 pi on 1 is the same as 8 pi on 4, where k equals 0, 1, 2, etc. Therefore, z, to get z out of z cubed, I've got to raise it to the power of a third. So this would be square root of 8 to the power of third. Cis, a third of my angle, negative 3 pi plus 8k pi, and a third of this is going to be times by a third, which will make it a 1/12 on the bottom, where k equals 0, 1 or 2. So all of a sudden now our argument has been divided by 3. We've done a third of it. Now square root of 8 to the power of a third is square root of 2. Okay, because 8 to the third is 2. So it'll be square root of 2. Cis negative 3 pi plus 8k pi on 12. K equals 0, 1, 2, etc. Now, the question said to solve for z. We know we wanted 3 solutions. So what we do now is we say if k equals 0, our first solution, z1, k will equal 0, it'll be root 2 cis, if k is 0, we'll get negative 3 pi plus nothing over 12. Or root 2 cis, cancel down the 3/12, negative pi on 4. There's our first solution. If k equals 1, our second solution will be root 2 cis, k equals 1, we'll get negative 3 pi plus 8 times 1 is 8 pi divided by 12 equals root 2 cis, negative 3 pi plus 8 pi will be 5 pi on 12. Third solution, k equals 2, z3 will be root 2 cis, where are we? K equals 2, so we'll get negative 3 pi plus 8 2s are 16 pi all over 12. Let's simplify. Root 2 cis 13 pi on 12. Now have a think about where all of these solutions are. Let's draw them on one graph. The modulus, the distance from the origin, is all the same. So let's graph where this solution is, this solution and this solution. This one's at minus pi on 4. Minus pi on 4 will be down there. So one of them's here. Root 2 out from the origin. There's Z1. Z2 is at 5 pi on 12. 5 pi on 12. This is 12 pi on 12. Sorry, I didn't realise you couldn't see. So Z1 there at minus pi on 4, coming back this way. The second one, 5 pi on 12. If that's 12 pi on 12, this will be 6 pi on 12, or half of that. So 5 pi on 12 is going to be somewhere up here, where that angle there is 5 pi on 12. And our last solution is at 13 pi on 12. If this is 12 pi on 12, 13 pi on 12 is going to be out this way. Now, before I point something out here, we just need to finish this off, because this 13 pi on 12 is outside what we call our principal argument. Remember, our principal argument cannot go past the pi. If we go too far that way, it's quicker to come backwards. So this way coming back, this gap here is pi on 12. So coming back is going to be negative 11 pi on 12. So this solution, instead of writing it like this, we'd actually write it as cis negative 11 pi on 12. Technically that one's right, but this is according to the principal argument. Now, if we'd done this to scale, or even just the scale that I've done it there, hopefully you can notice something about each of these three solutions. There's one solution there, one solution there, one solution there. Their modulus is always root 2. So they're always root 2 out from the center. So each of those lines should be the same length. And what you should see, if you work it out, you'll see that the angle between all three solutions will actually be the same. Let's just, if you can follow me very quickly here, this is pi on 4, so this is really 3 pi on 12 is this angle. And this is 5 pi on 12. So altogether between this solution and this solution is 3 pi on 12 plus 5 pi on 12 is 8 pi on 12 is that whole angle. The angle here, you've got 1 pi on 12 there, 6 pi on 12 there, so that's 7, plus 1 more here, so that whole angle is 8 pi on 12. And then this whole angle here, this is 5 pi, sorry, this is 3 pi on 12 here. And this one here is 5 pi on 12. So all up, 8 pi on 12. So you can see that it's pretty neat how the solutions divide up the circle evenly. If there's 3 solutions, the angle between all the solutions is 1/3 of a full circle. If there were 4 solutions, then it would be actually 90 degrees between each of the solutions. So pretty neat how that works. So there we have an example of finding the solutions to a complex equation where we wouldn't otherwise have expected to get possibly all 3 solutions, but here they are, 1, 2 and 3. Of course, these are written in polar form. You could use your conversion techniques, your r-cis theta, to convert them back to Cartesian form and actually find it in terms of a plus bi. But we are not going to be doing that with this particular question. Alright, we may do one more example in the next video.